Okay, so is it visible?
Yes, sir. Yes.
Yes, sir.
Okay.
Yes, sir.
Okay, so again, I will say thank you, Mr. Sanket, for introducing me in front of the audience. So today my topic is a wearable or body-worn antenna solutions for defense and medical sector. So in this topic, we will see I will discuss little bit about introduction of RFID, which is radio frequency identification. Then I will discuss about the wearable antennas for UHF RFID system. Then I will tell that why we choose this UHF RFID for a particular application. Then we will see the main things in this topic, which is design consideration and challenges, which is actually more important than design any antenna development, because develop an antenna is not a difficult task, but to make that antenna and put it on a human body and to get the acceptable performance, which is a difficult task. So we will see all the design consideration and challenges in developing body worn antennas. Then we will see the EM part of that, how we see the performance of antenna. So antenna may be radiating in near field or far field. So what parameter we consider for the near field and what parameter we consider for far field. So we will discuss in this presentation. A prototype, I have a few prototypes, so I will show you. Then we will also see the experimental characterization, how we characterize these kind of antennas for communication. So here we are considering a case of RFID communication, the measurement of antenna parameters and near and far field. Okay, if time permits, then I will also discuss antennas for automotive. So we will start with the application. So here you can see this patient is lying on a bed in a hospital. So you can see here there are various leads connected to his body. So these actually leads are monitoring leads where we can find out the sugar level and other vital signs. Okay. So in this case, you can see here if there are a lot of leads, then it is very difficult for this patient to move, right? So in this case, what we can do, if we are able to integrate any antenna with his cloth and we can remove these leads, then we can improve his movement. Okay, so these kind of antennas or integrated antennas with cloth will helpful for various applications. So this is one application in medical healthcare. There can be any other applications like in defense sector, so that if we can see that soldiers are in a mission. Okay, so for tracking purpose normally we use GPS, but if you see some locations like remote locations and where GPS signal is not there, then we can use RFID technology for detect our soldiers. So if we have some close area or maybe small area, then we can track our soldiers by using this RFID technology. So that in that case, we can put RFID tag on a soldier, maybe soldier's cloth or soldier's beret, okay, so that we can track their location. If you see nowadays, RFID technology has widely been deployed for short distance communication within ultra high frequency band. So the ultra high frequency band is very useful for various applications. Why? Because frequency band is around 900 megahertz. So we can realize antenna of some centimeter size. So if you see at 1 gigahertz or 900 megahertz, the wavelength of that frequency is around 30 to 35 centimeter. Okay, so in this frequency range, we can develop an antenna of some finite size, or we can say a compact size. Okay, so there are other frequency bands of RFID. One is in kilohertz, another is in megahertz. So megahertz band is 13.56, so which is actually very low. If you design an antenna at 13.56 megahertz, it will be a very big antenna. Okay, so it is not feasible for realization. So if you see, the RFID systems find several applications in industrial and commercial areas such as toll collection, right? We all know that electronic toll collections, we can use RFID. And nowadays in India also, pupils are using this technology. For libraries, for animal tracking, vehicle security and healthcare due to their attractive features such as high data rates, good read range and low cost. So all these features we will see in this talk. Of particular interest are RFID systems for IoT-based personal healthcare application and specifically those applications where RFID antenna and sensors are integrated in a smart glove. So when we have a normal glove, we can integrate antenna with RFID reader, then we can call this as a smart glove. So this whole presentation will be more on smart glove. Okay. So if you see the RFID applications, so in identification, tracking for logistics, asset management, access control, payment, product tracking. So there are various applications of RFID. So in India, we are moving to RFID technology. And when you go to Decathlon store, then you will find some objects. So on that objects, RFID tag is there. Okay, so when you will uh, leave the Decathlon store, you don't need to wait for the payment. Payment will cut automatically. So that this technology is very helpful for various things. I consider here few antennas which we have developed at Microwave Radiation Laboratory at University of Pisa, Italy. So these antennas all are radiating around 900 megahertz, okay, which is UHF RFID band. So this UHF RFID band is different for different countries. So India and Europe shared the same frequency band, which is 865 megahertz. In United States, it is around 920 megahertz. So if we develop any antenna which can resonate from 850 to 950 megahertz, then we can cover the whole globe. Okay? So we can make a general antenna so that it can be used in any country. So you can see here the size and you can have some idea at 900 megahertz what is the size of this antenna. So it is not very compact, right? But these antennas are for designed for RFID reader. So RFID reader is having a large size, so we can fit this antenna. But when you see these antennas for RFID tag, so this you can see here, this RFID tag is very small, right? So here we are using a dipole antenna. So dipole antenna is a simple antenna. We can make some modifications. So if we have some limited size, we can meander this dipole antenna. So here in this case, in the right hand side picture, you can see this is some meandering. So meandering is actually gives the less size of the whole device. Okay, so we can fit any dipole antenna which is radiating at 920 or 868 megahertz in a small area. Okay, so nowadays in smart cars also this dipole antenna is there. Other than this dipole antenna, there is an chip which is application specific IC. Okay, so this specific application specific IC has lot of components. Okay, so I will discuss few components of this application specific IC. Okay. So if we see the communication, how communication happens in RFID, so we have RFID reader, which we connect RFID reader to an antenna, right? Then we can transmit or send a signal to RFID tag. So this tag will take that power. Okay, so this chip will receive this power through antenna and this power will go to this chip. So in this chip, the first component is rectifier circuit. So rectifier is actually convert RF into DC. So for RF power, we are receiving from RFID reader and we are converting this RF to DC. So this DC is actually used for other components like modulator, demodulator, logic, memories are there in this chip. So all these components can work with this DC value because this in this picture we are showing a passive tag. Okay? So in passive tag there is no battery. So this chip excites by receiving power from the RFID reader, which is coming from the outside. So if you see, I put here some challenges in designing wearable antennas. So here the first challenge is very big challenge is human body near field effect. So here we will discuss the human body, how we consider the human body for that. Because let's take an assumption that we are making an antenna on some substrate. Okay, then we use the same antenna. If we put on a human body, it may change their performance. Okay? So the performance of this antenna may change when we put on its human body. So the human body effect come from the dielectric and conductive property of the human tissue layer. Okay, so here if we suppose I take an example of hand. Okay, so we have human, we have one hand. Okay, if we want to place an antenna on a human hand, okay, then we have to model the human hand in any electromagnetic simulator. Okay, so for that, what we need different, all the specification of these tissue layers. So there are different tissue layers like skin, fat, muscle, bone. Okay, so we have to know the all specification of these layers. So these layers have different dielectric constant and different conductivity. Okay, so because of the dielectric constant and conductivity, it changes the antenna resonance frequency, or we can say that input impedance of the antenna. So whole change may change. Okay, so this is actually the human body effect, and it may be vary. It depends on the antenna radiator shape, which kind of antenna we are putting on a human body. Okay, suppose we are putting an antenna like patch where we have a ground plane on the back side. If we put on a human body, it will affect less. Okay, because there is a ground plane, so there is no radiation below the ground plane. But if we have an antenna like dipole, okay, then this antenna will be affected much from the human body, because it is dielectric is directly in contact with the antenna. So this will keep the antenna efficiency high and increase battery lifetime by using an ground plane. Okay, but every time we cannot place a ground plane. This thing we will see by taking one example. Okay, one application scenario we will see. Then we will look for the type of radiator, which type of radiator will be helpful for that particular application. Second thing is compactness. Okay, so the compactness is necessary because suppose I want to put an antenna on a human hand, which is actually on the back of a palm. Okay, then we know that palm size. Then we cannot make an antenna which may be more than the palm size. We have to fit in the palm, so that we have to go for compact size. But if we make antenna compact, its efficiency will degrade. Okay, so we have to compromise the size and performance. The next point is desired radiation characteristic. Okay, so what type of radiation characteristic we need? This we know the application. Okay, so based on the application, we can choose the radiation characteristic, and based on the radiation characteristic, we can choose the antenna type, radiator type. Another thing is, whatever the antenna is having some radiation characteristic, when we put on a human body, its radiation properties also change. So sometimes if you are putting a patch antenna, okay, it is radiating in the normal direction. But when you put on a human hand, it may radiate in different direction. So it is actually the study of human hand in a software. Okay, although we can do the measurements, but we have to understand things before developing it, because it is very difficult to do things after development. So the low cost and lightweight, so this is another point for commercialize our product. If it will be a low cost, then people will buy it. Lightweight, we are putting an antenna on a human hand, it should be lightweight, otherwise our hand will face some problem. Okay. Another point which is giving from FCC. Okay, so FCC regulations on SAR value. SAR is actually the specific absorption rate. Okay, so this SAR value will always be there when we have any electronic component and it is proximity in the human body. Okay. So suppose I take an example of mobile phone. So mobile phone has antennas inside. So there is always a SAR value which is given by the FCC. Okay, so this SAR value tells us we cannot transmit more than that power. Otherwise, our tissue layers will be affected much. Okay, so this SAR value is fixed from by the FCC. So next point is impedance matching and antenna detuning. So this case I was discussed. If we are making or developing any antenna on air, so I'm saying here air, but this antenna is actually printed on a cloth. Okay? When we put this antenna on a human hand, then it needs to consider the human body effect, because whatever the performance we are getting from this antenna, and when we see this performance, it will change. Okay? Another point is the stable performance. Okay, so we need stable performance in any case. Okay, so here we are seeing a case of bending and stretching. Suppose we bend our hand, okay, or maybe we stretch this glove or cloth, then this shape may affected. Okay, so by changing this bending and stretching, its performance should not change. Otherwise, there is no use to put an antenna on a human head. Okay? So it should work in all scenarios. In order to increase the battery life, antenna must be efficient. So if you see the practical thing, here we have antenna. This is RFID reader antenna. We can put RFID reader somewhere here. Okay? So if we put RFID reader here, so nowadays you can get RFID reader which is very compact, portable size, like wristwatch. Okay, so we can connect this antenna to RFID reader. Then this RFID reader is heavy. Okay, so this battery is transmitting signal. So if we have this antenna which is not very good or not having very good performance, then this battery will drain out fast. Okay, so for commercial application, it will not be a suitable. Safety guidelines, which is actually the specific absorption ratio. How we calculate the SAR? There is a standard formula, sigma E square by rho. So E is the main factor. E is the electric field. Okay, so whatever the field our antenna is resonating or it transmitting, we can find out the E value. Okay, so in simulation nowadays we have a electromagnetic software. We can see very easily these values, so that we can find out the SAR distribution. In United States, the SAR limit is 1.6 watt per kg averaged over the 1 gram of tissue. In European Union, the SAR limit is 2 watt per kg averaged over the 10 gram of tissue. So these are actually the standards where how we find out the SAR value, which is actually the fixed by the FCC. In India, earlier it was uh, working with the EU limits, but now it switched from EU to US limits after 2012. But it is not very much different values. If you find out the 10 gram tissue or 1 gram tissue, it will be more or less same. Okay? But there are some different rules for different countries. So based on that, the calculation limit is different. So how we consider the human body effect? Okay, so what happens? Resonance frequency changes when antenna come in the proximity to the human body. Okay? So in order to consider the body effects, a body phantom should be included in the design process. So whenever we design any antenna, we have to consider this body phantom. Okay, so this body phantom, how we can make it? So if you see, if you know, tissue layers are there. First layer is the skin, then below skin is fat, muscle and bone, right? Then what is the thickness of this skin, fat, muscle and bone layers? We have to see this. So this may vary from pupils to pupils, right? But here we are considering a general thing. Skin we have taken 2 mm, and other these three layers we have taken 2 mm, and bone is 10 mm. Okay? So this some data we can get from the biomedical engineers. They are doing work on this. So this information we got from the biomedical engineers. If you see here the conductivity at 868 megahertz, okay? So for skin, fat, muscle, bone, it is different. Okay, Dielectric constant you can see here is for skin, it is 41. Okay. Normally we design our antenna at dielectric constant which is around 2.2 or 3, okay, or maybe 4. So FR4 has a dielectric constant which is 4.3. So if we design an antenna on a FR4 and if we put antenna on this dielectric constant, so the resonance frequency will change. Okay, and this change will be maybe more. Okay, because the dielectric constant is very high on the top layer. So this dielectric will include it with this FR4 dielectric constant. So in this case, we have to consider this effect before developing any antenna. Otherwise, what happens? We develop an antenna on FR4. When we put on a human body, it will not give anything. Okay, so the resonance frequency will shift downwards. Maybe initially we designed this 868 megahertz antenna, and when we put this on a human body, we achieve 720 megahertz. So now we can see that 150 megahertz shift we observed in this antenna. Okay, so this actually we have to consider this thing. Again, another point is if you see the conductivity and dielectric constant at different frequency. Okay, so here we are seeing at 868 megahertz. Suppose I want to design an antenna which is dual band. Okay, so one is operating at 868, another frequency is 2.45 gigahertz. In this case, if you see the conductivity at 2.45 is changed. Okay, 868 conductivity was 0.85 for the same layer, and now it is 1.46 at higher frequency. So it is changing. So if we want to design any dual band antenna, we have to simulate this thing also at this frequency. Okay, so it is not that simple that we are just simulating antenna at this frequency by putting these values. We have to see this effect also. Otherwise, what happens, this antenna will not work at 2.45 gigahertz. So here from this data, we can understand very well that it is very difficult to design broadband antenna for body worn application. Okay, because we don't know the information in between these frequencies. Suppose we want to design an antenna starting from 868 up to 2.45. So we have to simulate this antenna performance in the whole range, right? So in the whole range, we have to have these information first. Then we will simulate at each frequency from here to here. So it will be very difficult task. So that it is very difficult to design any broadband antenna for the wearable applications. Okay. There are some other this wearable antenna applications where human body is not in the picture. Then we can develop it or we can design it. Whenever we design this antenna for human body, then these factors will be there. We have to consider these factors. Now, if you see the relative permittivity of body tissues decreases with the increase of frequency. So when we are increasing, we are going at higher frequencies, our relative permittivity of body tissues decreases. Okay, so this is actually happens because of the structure of our tissue layers. Because of the lossy nature of human tissues, gain of the antenna reduces and human body absorbs radiated power. So when our body absorbs more radiation, it will convert in heat and it will be affected our body. Okay. So how we can do these things? Okay. So here we are modeling as this human hand as a lossy block. Okay. So we have antenna we can put on a lossy block. Here you can see in the right hand side picture, antenna is on air. Okay. So this lossy block we can model in the software. So compare the free space where no absorbing material, antenna efficiency with that of the antenna efficiency in the presence of an absorbing material. Okay. So this is the comparison where we are putting absorbing material here. Why we are saying absorbing material? Because this is a lossy block. So this is human hand. Human hand will absorb that RF power. Okay. So we can treat this human hand as a lossy block. Effects of bending on antenna performance. To check the stability of the antenna, bending is an important parameter to study. Okay, so the resonance frequency may shift, and this shift depends on the design of an antenna. Okay, so if suppose if you are putting one antenna like suppose this is a human hand. Okay, these are fingers. Okay? If you are putting antenna here in this place, okay, then if you bend or stretch your hand, this antenna will affect less. Okay, suppose if you put this antenna somewhere in the fingers, and if you move your fingers, okay, from straight to downwards, then the antenna position will change, or maybe the polarization of the antenna will change. Okay, so it is, we have to consider the all these environment, means environmental factors. Okay, so bending and stretching will always be there, because we cannot put our hand straight always full day. Okay, so that we have to choose the location of the antenna where it will be affected less from the other factors. Okay. So measurements on body, again it is necessary to measure the performance of the antenna when antenna is in proximity to the human body. Then we will get the real picture of the solution. So few things are available in the software. Suppose we can model this human hand, and here you can see, here we took some approximations. Okay, so this is not the exact thing what we are simulating, but we are taking consideration of these layers in the software, so that we will have some idea. We cannot say that we will get the exact value in the measurement, but here we are taking these thickness of the tissue layers, then we can get some nearer solutions. Okay, so whatever the resonance we will get in the measurement, it will be very near to the simulation, because we have considered this thing. But again, there is approximation. Some different human will wear this glove, then it may have different skin thickness. Okay, so if thickness will change, so some conductivity and dielectric constant will also change. Okay, so based on that dielectric constant change, we can have some frequency shift. Okay, but it will change little bit. Okay. Now we will see some advanced manufacturing processes for such kind of antennas. So here we are considering few techniques. First one is the fabric based embroidered antenna. So here you can see here, this is E-shaped patch. Okay, so this is actually developed on a cloth. So the white portion is cloth, and this E-shaped patch. So here this author is putting here my coaxial connector to feed this antenna. Okay, so this coaxial connector, this is the back side of that. So these people solder it. Okay, so it is actually not soldered, they are putting epoxy material. Okay, so one thing is, we cannot solder any connector to antenna which is actually designed on a cloth. Okay, otherwise what happen when we do solder, then the cloth will burn out. Okay? Because of the heating, this cloth will burn. So that this solution is not suitable. We cannot solder, we cannot use solder for such kind of antennas. Okay, so there is a epoxy glue. Okay, so the epoxy is actually the semi liquid thing. When you put it, then after some time with the reaction, it will react with air and it will be become hard. Okay, and once it is hard, it will be conductive. So this epoxy pupils used for this kind of antennas. But again, this epoxy is not very good. So after some time, after using these antennas, this epoxy will remove. Okay, so this connector will be detached from this uh, back side. Okay, so this is actually the some challenges. If you see the second polymer embedded antenna, so here this antenna is designed on a polymer material. Okay, so if you are designing an antenna on a polymer substrate, we can bend it very easily. Okay, I'm not talking about here the performance, I'm just talking about the techniques, manufacturing processes. Okay, so this kind of processes are available, so that we can fabricate our antenna, we can bend it very easily. Okay, inkjet printed antenna. So this antenna is actually inkjet printed. So this is actually a very thin material. This is like paper material. Okay, so we can bend very easily this antenna. Okay, This is another antenna designed using screen printing. Okay, so this is textile antenna. Okay, so this is again designed on a cloth. So here we took a zoomed picture of this transition. Okay, so here this is the portion where we are connecting a coaxial connector and feed. Okay, so if you see this zoomed part, you can see the cracks on the surface of the antenna. Okay, so this antenna is actually used for commercial purposes. So this antenna, people can make it wash, and after dry it, it should work again. Okay, so if you wash any antenna and dry it, then again you are using, then the performance should not change. Okay, so this is the motive of developing antenna for commercial purpose, because the solution must be reliable. Okay, so because of this issue, cracks and other thing, what we got, connector detachment. Okay, so this connector may detach from this feed line. So what happens if we are getting these cracks? It increases the ohmic losses. So ohmic loss will increase, then we will have more heat and the gain of the antenna will reduce. So what is the solution for such antennas? Coating with a thermoplastic material. Okay, if we coat this antenna on a thermoplastic material, then we can improve this antenna performance. Okay, but again, this is not a very perfect solution. Again, after some time, it will not work. Now, if you see, these are the textile antennas. Okay, so textile antennas are a special class of antennas that are partially or entirely made out of textile materials. Okay, so there are available materials in the market. If you see, these are dielectric fabrics: cotton, polyester, silk, jeans. There are various other also. I just consider these 3 or 4 materials because people are using these materials. There are conductive fabrics to make tracks. Okay, so zelt, flectron, copper, polyester fabrics. So these fabrics are used as a conductive fabrics, so that we can by using both fabrics, conductive and dielectric, we can realize textile antennas. So we discussed so many factors till now, but if you see, there are other factors also which influence the antenna performance. What are the parameters? One is the thickness of the fabric. Okay, so once you purchase any fabric from any manufacturer, so the thickness of that fabric should be same. Okay, so if thickness of this fabric will change, then your performance of antenna or any electronic component will change. Okay, so thickness should be same for the whole fabric. Another point is complex permittivity. So if we have a dielectric constant, it will have complex parameter. Okay, so the complex part gives us a loss. So we want this complex part should be very, very less. Next is the surface resistivity of the conductive textile. Okay, so we are using this conductive textile. It is not perfect electric conductor where we can get the conductivity which is infinite. Okay, so this is practical conductive textiles. We have some surface resistivity. Okay, so because of that surface resistivity, the gain of the antenna will not be improved. Okay, so with this resistivity, some loss will be there because of the some heating. Okay, so this supplied power or whatever power we are supplying to the antenna, it will convert in heat. Okay, because of this surface resistivity, and this surface resistivity value changes for different conductive fabrics. Okay, loss tangent. Loss tangent is an important factor. In previous talks also we people discuss about this loss tangent. Okay, so it tells the we can say the performance of this dielectric sheet. Okay, so if loss tangent is very, very less, then we have very less loss in that dielectric. Otherwise, if you see the commercial purpose, normally we use FR4 substrate. So if we are using FR4 substrate, then loss tangent will be is very, very high. So loss will be more. But again, it depends on the frequency. Okay, if you are using FR4 at low frequency, like in this frequency 868 megahertz or 2.45 gigahertz, FR4 gives a good result. Okay, So we can use FR4 for such kind of antennas, because in this application, if you see, we will go for the low cost solution. So low cost solution we cannot develop from some very good substrate, Roger substrate or other substrate, right? So that's why we are using cloths here, because cloths are more cheap. Another point, last point, is mechanical deformation of the fabric. Okay, so this should not be there. If mechanical deformation is there in the fabric, then we cannot do anything, right? So we have to choose a good fabric for development. So if you see the electrical properties of conductive textiles, it has been accurately characterized using these three methods. So these are available methods where we can characterize our conductive textiles. Okay, so transmission line method is there, which is very common. Cavity method, MOM method. So if anybody is interested, you can go with this method, or if you ask me, then I will send you some documents for these methods. Okay. Their surface resistivity are often given by specialized producers. Okay. So this surface resistivity value we can get from the manufacturer, okay, as a data sheet. Specific conductive textiles, sometimes designated electrotextile. Okay. Those are commercially available, have been successfully used in developing antennas. So we call these textile as a electrotextile, because this textile is having some electrical property, and we can characterize these fabrics, so that we can call this textile as a electrotextile. So I have put one reference here. This is actually guidelines for the choice of materials for the design of textile antenna. Okay. So for textile antenna, there are there are various materials. So we can see the choice of materials in this survey. Okay. So this is actually the survey where people are developing wearable antennas. So there are a lot of materials are there. Which material can be used for which application? You can refer this paper. So if we see the wearable antennas for UHF RFID, okay. So in this first picture in the left hand side, if you will see here, this antenna is designed on a FR4 substrate, okay, which is low cost substrate. So this is a loop kind of structure. Okay. So this loop antenna is there, but it is not exactly the same loop which we have. Okay, just wait. So this is not this kind of loop, right? So here you can see some capacitors are inserted. Okay. So these capacitors can be lumped capacitor, can be chip capacitor, or can be interdigital capacitor. So here pupils are putting the interdigital capacitor. Okay. So why they insert interdigital capacitor? Because they can just make a simple loop like here. Okay. But what happened? If you see the size of this size of the loop is comparable to lambda or more than lambda. So what happens if it is comparable to lambda? Then we will have surface current distribution which will be in the out of phase. Okay. So suppose surface current is traveling in this direction. Okay. Suppose surface current is traveling in this direction, and surface current will travel from here to here. So it will oppose this surface current because of this length, because nulls will be there. We know that after 180-degree path length, phase shift will be there. Okay. So because of this phase shift, we are getting out of phase surface current. Okay. So these capacitors will change the phase of the surface current, so that we can get in phase surface current on the whole loop. Okay. So why these people did this? They want to achieve a high magnetic field along this plane. Okay. So one can achieve a high magnetic field by making this surface current in phase. Okay, so this is the main idea of this. So there are various available papers on this technology. So some people will put a lumped capacitor here. Some people will make a capacitor from the microstrip lines, printed lines. Okay. There is another antenna here, which is quasi-Yagi antenna. Okay. So Yagi-Uda antenna, we all know. We have used Yagi-Uda antenna in our previous times. okay, where we have a driven element and one reflector, and there are so many directors. Okay, but here you can see I'm calling this as a quasi-Yagi Uda antenna. Why quasi-Yagi? Because we are not considering all the situations here. We are not taking reflector, we are considering here only the driven element and director. Okay, so that we can call this as a quasi-Yagi. Quasi-Yagi means it is not perfectly Yagi, but it is more similar, or it will give the more or less same performance as Yagi gives. There are few more antennas here. So in this you can see here UHF tag antenna for near field and far field RFID application. Here you can see the size of this antenna is 6 centimeter or 6.5 centimeter. So this antenna is actually the meander dipole antenna, right? So this is actually printed on a some thin substrate. Again, this substrate is a thin, but it is not flexible. Okay, so there is a limitation of movement of this. We cannot bend fully this substrate. This what we discussed in the previous slide. So these 1 picofarad capacitor is actually the lumped capacitor. So instead of interdigital capacitor, we can put these kind of lumped components here. Okay, so that we can make such kind of loop antenna. This is again a loop antenna for UHF near field RFID application. Okay, so this is actually the band. So this band is actually gives a 180-degree phase shift. Okay, so by getting 180-degree phase shift, we can make surface current in phase, so that we can get the magnetic field which will be higher in this plane. There are a few other antenna here. You can see this is first picture of this wearable dipole antenna. Okay, so this dipole antenna is integrated with this clock. Okay, so this is the size of this antenna. It is not very. It is actually, we can say this is compact antenna. Okay? We can compare with this glove. Okay, we can fit very easily on a human glove or human hand. Here this antenna on the below. Here it is again a quasi-Yagi antenna for UHF RFID reader. Okay. So as I mentioned that for RFID reader, we can make bigger antennas because we have space. We will put our RFID reader somewhere, maybe in on the wall. Okay. Suppose we are doing some application of library. We want to track our books in library, then we can put RFID reader on some wall and we can put RFID tag on books. Okay, so in that case, on wall we can put this RFID or bigger size of antenna, but we cannot put this antenna for the book. Okay, otherwise it will take more space. So we can make this antenna for book and this antenna for the tracking purpose. So maybe we can fix it on the wall. There is another kind of antenna. So this is wrist worn antenna. Okay, so wrist worn antenna, we can put it here. This is actually the dipole antenna, and this is printed on a thin substrate so that pupils can bend it. Okay. Again, this substrate has some limitation. Okay, although it is very thin, but if you use this antenna for longer time, this substrate will break. So till now, what we saw, if we are developing an antenna for human hand, then we have some specific positions. Okay, so suppose in the first picture you will see here you can make an patch antenna. Okay, then you can put it on the palm so that it will be less affected from the bending, stretching, all these factors. Another position is along the this. Okay, so this is kind of solenoid antenna or loop antenna. So this is actually the wristband antenna. Okay, so as a wristwatch we can make it like this. Third is we can choose any other antenna like dipole, Yagi-Uda antenna on the top of the palm. Okay. There are other positions also, but we cannot put these kind of antenna on some other different places because otherwise it will affect much. Okay, while uh, doing some bending and stretching things. So now we are discussing here one application scenario. So this application scenario, this antenna was developed for warehouses. Okay, so there are laborers in where those are working in warehouses. They will wear this smart glove and they will track some objects. Okay, suppose let's consider a case where we have one bigger box, and in that box there are multiple items. Okay, suppose let's say 100 item is there. We want to track all these items and we can make a list of that. Okay, so one way is to do this thing is manually, one by one person can remove or count these items and note down. Okay, another way is by using RFID technology, so that person can wear a smart glove and they can detect all the objects in seconds. Okay, so here the situation is he can wear UHF RFID reader here like wristwatch. Here you can see one example of this RFID reader. So RFID reader nowadays are available in the form of wristwatch. So we can put this wristwatch here. Then we can connect this wristwatch to this antenna. Okay. So if we have a suppose patch antenna or dipole antenna or any Yagiuda antenna, we can put it here. We can make a connection and we can transmit that signal. Okay. So if we transmit a signal, some tagged objects are there or maybe RFID tag, it will detect. Okay. So the application is we want to detect some objects which are in the range of 30 to 40 centimeter. Okay. So up to 40 centimeter, we want to detect objects. Same time, we want to avoid objects which are far from 40 centimeter. Okay, so we don't want to detect these objects. Okay, suppose I want to detect only objects which are in a box. Okay, in that case, we have to fix the power so that radiation will not go far from this box. Okay, so in this way, we can choose the transmitted power of this RFID reader. We can select that power. So this is the actually application scenario. So now for this application scenario, we have to choose our antenna shape. What type of antenna we will use here? Suppose if we take here patch antenna, okay, then if we put a patch antenna here, then what happen? There is a ground plane on the back side. This patch antenna will radiate in this direction. Okay, so we know that our objects are in this direction and in this direction. Then we don't want any radiation along this. Okay, so this is actually the waste radiation. We will not get any detection by putting a microstrip patch antenna here. We can choose different shape which can radiate in this direction and in this direction. Okay, so for this people use the wristband antenna like loop antenna or solenoid antenna. So here you can see this is one solenoid antenna or you can treat as a loop antenna. Okay, because the function of solenoid and loop are same. So this loop antenna radiates along the axis. Okay, so this is the front side and this is the back side. So it will radiate along this axis. But for this application, if we are putting this solenoid antenna here, okay, then this radiation will go here, right? We want radiation only in this direction. We don't want radiation in along this direction because whatever the radiation will go here, it will affect this human body or it is actually the waste. Okay, so we can save our power. Okay? So in this way, for such application, we choose a different layout, which is Yagi-like antenna. Okay, so this is actually the driven element, and there we are putting these two directors. Okay, so these are compact directors because we know that we have to put this antenna on a back of a palm so that we cannot increase the size of this antenna. Okay, so we have to fix it on the human hand. Discussed, we want radiation along the palm, this side and this side. Okay, so if you see, we consider consider initial am I audible? It is showing that I am muted.
Yes, sir. Yes, you're
Sir,
audible.
Now
now
you are
you are
audible.
audible.
Now you are audible, sir.
Okay, fine.
Previously, for last
So
2 to
actually
3
you're
minutes.
not audible.
Okay. So I have to discuss again the
Hello?
last slide.
Sir,
Yes,
previous
sir.
slide.
You
Previous
can
slide.
repeat.
Okay. Okay. Fine. Okay. So one thing is, any participant have any question, then you can ask in between also, so that we will move next. Till now, if you have any question, you can ask.
Sir, I have one simple question. Like,
Yes, ma'am.
if we are using any cloth, any cloth material, so how we can decide whether we should use cotton material or silk material? So what is the
Mhm.
criteria of selection of it?
Actually, the selection is first thing is we have to know the property, electrical property of that cloth, we can say. Okay. So this cloth, if it is very thin, then we design an antenna and then we put ground plane on the backside. Then what happen? Suppose we can just take an example of microstrip patch antenna. Okay. If we are having very less thickness of this substrate, then this patch will not have any gain. Okay, so this patch antenna will be a lossy antenna. So
Okay.
if you find out the gain of this patch antenna, it will be in negative, maybe minus 8 dB or minus 10 dB value. Okay, so for that purpose, suppose if you want to uh, use some different radiator like dipole antenna where you don't have any ground plane on the backside, right? Then you can use such kind of fabric, which is thin fabric or thick fabric. All fabrics will be used. But for a antenna which you have a ground plane on the backside, you cannot use very thin fabric. Okay, so jeans fabric, that's why people use, because this jeans fabric has some thickness. Okay, because it is more thick compared to this very silk cloth and other cloths. So it depends on the property. Okay, what epsilon r value is there, what is the thickness of this material, and yeah, for dielectric thing we have to consider these two things only. So 10 delta can be maybe vary, maybe it may be low or it may be high, but two things we have to consider. One is the thickness and other is the dielectric constant. So if you see, if you find out the dielectric constant of such cloths, it will be more or less 1.5, 2, or maybe 2.3. Okay, so it is actually useful for antenna, because for antenna we need less dielectric constant. So major factor is thickness of this dielectric fabric. If this dielectric fabric thickness is very less, then our selection of radiator will be more important.
Okay. Thank you, sir.
Thank you. Any other question?
Yes, sir. Good evening, sir.
Yeah, good evening.
Sir, my question is related to the far field, sir. Sir, usually we prefer that antennas to work in far field, but sir, how can we make these variable antennas to work in far field, or sir, is that knowingly we want that these antennas should work in near field region?
Yes, okay. So this thing I will discuss in the presentation. So this antenna will be used for not only for near field, it will be used for far field as well. Okay. But the problem is, suppose if you want to use this antenna in near field, then you have to consider the parameters. Okay. By getting the parameters, we can say that this antenna is useful. Okay, so these parameters are different for different application. Like for near field, we cannot consider the radiation pattern and gain of the antenna. Okay. In the near field region, we have to consider the electric field and magnetic field strength. So on the basis of electric field value and magnetic field value, we can say that this antenna will perform or not. Okay. In the far field region, we consider radiation pattern and gain. Okay, we never consider the electric field and magnetic field because the dominant effect of these field parameters will be different. So initially at the near the antenna, it is actually the spherical waves. Okay, but in the far field, you will see that it converted the spherical wave into plane wave. Okay, so the parameters, the performance parameters changes when we change from near field to far field. So the same antenna can work for the far field as well. But in
Sir, you are not audible now, sir.
you have to consider electric field strength and magnetic. You need a strong magnetic field if surface current is in.
You are not audible.
Your voice is breaking, sir.
Yeah, I will check my connection. Now I am audible.
Yes,
Yes,
Sir.
Okay. So what I was discussing about, the near field parameters are different and far field parameters are different. So we have to consider near field parameters like electric field and magnetic field if we are using the antenna in near field. If we are using the same antenna for the far field, then we have to consider the radiation pattern and gain. Okay. So these are two different things for near field and far field region, but it doesn't you cannot say that this antenna is working only in the near field region. So it depends on the performance parameters. So we will see here all the parameters in the near field and far field. Okay, is it fine?
Yes, sir. Clear, sir.
Okay, so that's why we have to make this antenna, which was a straight one, we have make it folded. Okay, so that we can have surface current which is in phase. So because of this in phase surface current, we will have a strong magnetic field near this antenna. Okay, so in the region where we have palm, okay, so in near the palm we have more magnetic field. So this antenna is a combination of Yagi-Uda and the loop antenna. Okay. So in the near the palm, we are detecting our objects through magnetic field, and along the finger, we are using electric field. Okay. So electric field is more. Okay, I'm making this presentation in a bigger slide. Yeah. So here we are using two field strength for detecting our objects. Okay, so this loop will give us a magnetic field, and this Yagi-Uda antenna, which is combination of loop and this director, will give us a strong electric field. So this is the antenna is a combination of loop and Yagi. So this is the fabricated picture. I will talk about this again. Okay, here you can see the reflection coefficient of this antenna. Okay. So the S11 value shows us the reflection coefficient. So for antenna to be acceptable value is minus 10 dB. If it is minus 10 dB, then we can say that this antenna is performing well. So here in the simulation and measurement, you can see here the difference in simulation result and measurement result. Okay, so it is very much different from the simulation. So it is because of the what we approximated the values. Okay, because we consider the 2 mm, 2 mm and 10 mm thicknesses for different tissue layers. Okay, and this practical scenario is little bit different. Okay, so this coaxial cable here you can see which is connected. We didn't consider this cable in the simulation. Okay, so because of this cable, there may be some radiation effect. Okay, so because of that, this frequency is shifted little bit. So, but if you see the frequency which we are using at 868 megahertz, this S11 value is below minus 10 dB. Okay, so it is acceptable so that we can go for this solution. Okay. These are the SAR calculations. So these all the pictures taken from CST Microwave Studio. Okay. So this first picture, if you see here, this is hand, which is actually modeled in a CST software, and we simulated this SAR value here. Okay, so the red portion you can see here, it is more radiated. Okay, so the radiated part is here. The value we can read from here, and after getting the SAR value, we can find out the PT max, which is actually the transmitted power of the reader. Okay? So we are allowed to transmit this much power. We are not allowed to transmit more than PT max. So this PT max is decided by the SAR value, okay, which we can calculate in the software. So this is the human hand where different layers, different colors you can see here. So these colors are for different layers. Okay, skin, then fat, muscle, bone, then again it is repeats because our human hand is like that. This patch antenna or this kind of or any kind of antenna, you can put it on the top and you can make some simulations. So this I have discussed already, so I will not discuss again. Okay. Again, these are the pictures taken from CST Microwave Studio. How we can give this information to software. Okay, so whenever you people will come to offline sessions, then we will have hands-on for this. We can give the density of layers in the software. So this raw value is for skin. Okay, so 1109 kilogram per meter cube is the value for skin. So density we have to put. Then we can find out the power loss density in the software so that we can find out the SAR value. Okay. Frequency we can choose at what frequency we want to calculate it. So it is the thing which is actually we can do in the software. These are the electric and magnetic field strength. Okay, because I mentioned this antenna is for near field application. So we are considering here the electric field and magnetic field strength. Okay, so here this is the antenna. Here you can see the strength of this electric field and magnetic field. So this is the electric field and this is the magnetic field. Okay. So here you can see magnetic field is more or less same in both direction. Okay, because this Yagi Uda antenna, or we are putting here a director, this director will work for electric field, not for the magnetic field. So when we put director, then you can see the changes in the electric field strength. So electric field strength is increased along the fingers. Okay. If you compare on the back side to the front side, the electric field values are more along it. Okay. But magnetic field value is not changing. So we can understand that this effect is because of this director effect, and this antenna is actually the Yagi quasi Yagi antenna here. This is the measurement setup, how we can measure our performance of these kind of antennas. So this is a very simple measurement setup where we can connect one commercial RFID reader, okay, and this reader can be connected to computer. So we can see all these things in the computer. Now this RFID reader we can connect through a cable to this antenna, okay, and we can put some tag. Okay, so this is the picture of tag. We can put it maybe in the horizontal direction, vertical direction, and different directions, so that Now we can find out the distance. Okay. So what we will do, we will put this tag near to this prototype, then we will go far from the prototype. Okay. So when we go far from the prototype, the field value will decrease. Okay. So these are the pictures. If you see, these are the figures. These field values are decreasing when we go far from the prototype. Okay. So in this way, after some time, after some distance, it will not give any value. Okay. So it means it is not detecting the tag. Okay. So after some time, after some distance, it will stop detect. So this is the read range. So it is the read range from 0 to 14 or 15 centimeter. So up to 15 centimeter, we can detect our RFID tag. This is another measurement setup to see the field strength. Okay, so one port of vector network analyzer, we can put it to prototype. Another port we can connect to magnetic probe. So this magnetic probe, we can find out the magnetic field, right? So this magnetic probe is this. So this is actually the crude way of doing magnetic probe. Okay, this is not a standard probe. We make it through a coaxial cable. So what we did here, we remove the center conductor, okay, scratch the center conductor and connect to the outer part of that conductor. So that in this way we can make a loop here. So this small loop can work as a magnetic probe. Okay, so this magnetic probe we can use for the measurement purposes, and we can find out the S21 value from the VNA. So this S21 value is like this. Okay. So when we go from far from prototype, we put magnetic probe here, then we will have good strength. When we go far from this, then it will decrease. So these are the measurement setup. This is the crude way. This is the standard way of doing. Prototype, here we are showing two solutions. Okay, so this is the driven element and we are putting here two directors. Okay, so these conductive tracks, or we can say these metal tracks, are made from some different material which have some conductive properties, and this is printed on a cloth. Okay. One more thing you will observe here, we are connecting here snap button. We are not used SMA connector here, okay, because this antenna is designed on a cloth. We cannot make a solder here, so that we are using snap button. Snap buttons are normal button which we use in our t-shirt or shirts. Okay, so you all know about these snap button. So these snap buttons can be used at low frequencies. So we have tested these snap button. These snap button can work up to 3 gigahertz. Okay, after 3 gigahertz, it will give more loss. Okay, so if you connect one, we can test snap button. We can connect a microstrip line, 50 ohm microstrip line, and we can test these snap buttons performance. So we have tested performance up to 3 gigahertz. So up to, then we analyze that up to 2.45 gigahertz or different frequency band up to 3 gigahertz, we can use these snap buttons. So it will be a reliable solution. Okay, so one female button is here. The male button can be connected to the RFID reader. So we can make it connection or disconnection. Okay. So two solutions, what is the difference in these two? Here you can see this is the printed solution. Okay, so printed is actually 2D. So it is a very thin layer of conductive ink. Okay. In this solution, it is 3D. So it is actually have a more thickness compared to this. Okay, so what happens with solution 2? This solution 2 is having less surface resistivity compared to solution 1. Okay, so in this way, we can say solution 2 is better. But if you see the reliability of solution 1 is better than the solution 2, because this 3D part or this more thickness will change, or we can say that it will mechanically deform after some time. Okay, so the printed portion will be more reliable compared to the solution 2. So we go for this solution 1. Okay, it has some more resistivity compared to this, but this solution will be more reliable. Okay, so our application was we want to give a product which will be commercialized, okay, and which can be used by some persons. So that we will go for some reliable solution, not we will go for the perfect performance. Okay. So this is the compromise between the performance and the uh, reliability. So here I'm showing here some read range. So read range at 868 megahertz. Okay. So this is the antenna, right? This direction is fingertips and this direction is human arm. Okay. So in this direction, you can see here, this reader can detect up to 28 centimeter or 27 centimeter along the fingertips. Okay. But along the arm, if you see here, it is detect only up to 23 centimeter. Okay. So here the read range in all directions we are showing here. In fingertips direction, it is detecting up to 27 centimeter, and along the arm, it is 23 centimeter. Okay. Now we want to make it some different thing. We want to increase the strength along the fingertips, and we want to reduce the radiation, or we can see the field strength along the arm. Okay, we want to reduce it because it is actually waste. So how we will do that? We can put a reflector here and we can put one director, two director, or more directors. So in this way, we can get more field strength here and less field strength here. So we can save our power. So here, this is the picture of Yagi-Uda antenna with one reflector and one director. Okay. So if you see the size of this 7.1 centimeter by 6.5 centimeter. So it can easily be fitted on a human hand or palm of a human hand. This is the radiation pattern we are showing, but here in this application scenario, there is no means we cannot take this radiation pattern as a performance parameter. Okay? Because I mentioned that we are using this antenna in a near field region, we will consider only the electric field and magnetic field strength. So if you see the field strength, this is the magnetic field and this is the electric field. Now you can see the value of electric field along the fingertips and along the backside. Okay? So it is confined. So field is confined along the hand fingers. So in this way, we can get more field along the fingers so that we can detect our objects which may be at 30 centimeter or 40 centimeter by after reducing this field strength. So we are using this field here. Okay, so we are not changing the power or we are not transmitting more power. We are just directing the field. Okay, so that we can use the same power. So if you see the read range in this case, with the help of one director and one reflector, we can detect objects up to 40 centimeter, right? Or if you see here, earlier it was 23, now it is 17.5 centimeter. Okay, so it is reduced. So we are reducing the field strength in other directions and we are confining this field in this direction so that we can detect our objects which are actually up to 40 centimeter. Bending, this bending is actually happened in simulation. Okay, so in simulation we can do such kind of, we can see such kind of effects of bending and stretching of any element. Okay, so by uh, taking different bends, we achieve this reflection coefficient. So in this case, you can see the reflection coefficient is not changing much. Okay, it is not shifting. The frequency is not shifting. The depth is only changing. Okay, so because of this, this antenna is actually the compact size, and when we bend our hand, then this antenna size will always be same, or the shape will not change. Polarization will not change. So that's why we have this good, we are achieving this good performance in all cases. In stretching, we can put this antenna here. Actually it is not very clear in the picture. This is actually a cloth and on the top of this cloth there is a antenna. Okay, so we test this antenna practically. So three scenario we consider. In one scenario we took just this straight hand and we did some bending or stretching, then so full, or we can say the closed palm. Okay, so all these three scenario, if we see the reflection coefficient, in all cases we are getting acceptable value. Okay, so we can do these kind of stretching so that we can say that this antenna, we will get the stable performance from this solution. So this is the comparison of different layouts. So we have tried so many layouts. You can see here Yagi like antenna with one director, with two directors, with one reflector and one director, with one reflector and two directors. So you can see when we increase the element, the size of this antenna is increasing. Okay. So we go for this solution, this one. Because we know our application, we have to detect object up to 40 centimeter only, right? And the size of this antenna is 7.1 by 6.5. So it can be easily fitted on all human body. Okay. So palm size could be more or less same for all humans. This antenna is actually little bit bigger so that it will not be easily fitted. Okay. Although it is having good performance compared to this, but we didn't choose this because of the size. So this is actually commercial product. So we have to make it general dimension so that it will be easily fitted to all human beings. These are some photographs of the fabricated antenna. So we have integrated with the cloth, and then after wearing this antenna, we test it. Okay, so this is actually the, you can see here, these are two parallel coaxial cables. Okay, if you see normally one coaxial cable is coming from VNA. Okay, so what we are doing here, we are converting unbalanced feed to balanced feed, because this is a kind of dipole antenna. We have to give this balanced feed. Okay, so here this two parallel lines are treated as balloon, which is actually the balanced to unbalanced transformer. So the coaxial cable which is coming from VNA, it is unbalanced port, and here we have balanced port, so we are converting unbalanced to balanced. This normally we do for all kind of dipole antenna feeding. So these are some pictures. Now, if we increase little bit complexity in these antennas, okay, so the application scenario 2 is we are making or we are developing a dual band antenna. Okay, then what we will do, we will see the performance at both frequencies. So we have to consider the conductivity, we have to consider the dielectric constant for both. But what is the application of this dual band antenna? Okay, so what we will do here, we enable the glove integrated RFID reader to transmit collected data toward a management data center through a wireless local area network. So in this case, what we will do, we will use this antenna frequency band, which is actually 868 megahertz. We will collect the information through this band, and we will transmit this information at higher frequencies. Okay, so this frequency band is used for transmitting that data. Okay, because we can collect data at 868 megahertz and we can transmit it to different frequency band. So why 2.45 gigahertz? Because the same antenna can be more efficient at this frequency, because the antenna size, if it is comparable to lambda, it will be more efficient. Okay. So this was the idea by taking these two frequency bands. So what parameters we will study in this case? Electric and magnetic field distributions in the near field for the 868 megahertz band, far field radiation pattern and realized gain for WLAT band, which is 2.45 gigahertz. So we will consider these parameters for low frequency and these parameters for the higher frequency for the same antenna. Right. So same antenna can be used as near field or far field. This thing we have discussed, I will not discuss this. This is actually the dual band antenna. So the outer dipole is resonating at low frequency, which is 868 megahertz, and the inner dipole is resonating at 2.45 gigahertz, and it we can see very clearly from the surface current distribution. So this surface current distribution is at low frequency and this distribution is at high frequency. So by seeing the surface current, we can see that this antenna part is resonating at 2.45 and this antenna part is resonating at 868 megahertz. So these are a few results, simulated results. I will not discuss too much about this. This is just a input impedance of the antenna for both band. So this is single band antenna and this is dual band antenna. So here you can see the imaginary part of this antenna is 0 at two frequencies. So that we can say this antenna will resonate at two different frequencies. Okay. So by getting S parameter or by seeing the Z parameter, we can say that this antenna is resonating at that frequency band. And at read range at 868 megahertz, we can find out similar as the previous case. And for 2.45 gigahertz, we will find out the radiation pattern. Okay. So you can see here the radiation patterns at 2.45 gigahertz. So it is directional. Okay. So same antenna can be used for far field region and near field region. Here one important graph we have put here, which is actually gain versus sheet resistance. So this sheet resistance is actually the resistance of this conductive fabric. Okay, so if this resistance is more, then you can see the gain value. Okay, so gain is reducing. So if we are using very good conductive fabrics like less sheet resistance, then we can get more gain. Okay, so this is the figure. It will be helpful for any antenna designer to take sheet resistance of these conductive fabrics. This is a picture of portable RFID reader. So you can see it looks like a watch, wristwatch. Okay, so this is portable reader. It has battery and a transceiver circuit so that we can transmit that RF signal. This is one RFID reader, which is actually the fixed RFID reader, and it is bigger than this. Okay, so for commercial purpose or for testing purpose, we use this RFID readers. So this reader has maybe more channels like 2 channel, 4 channel or 8 channels. So we can do also the localization in RFID by using this RFID reader. So we will see few more things here. So as we discussed, radiation pattern is not really helpful for getting the performance of the overall UHF RFID smart glove. Okay, so when we are working at low size, or we can say that size is very compact. Okay, so that radiation pattern for near field region is not a performance parameter because the dimension of this antenna is less than lambda. If it is comparable to lambda, then it will radiate it, or we can say that it will be a efficient radiator. But in this scenario, this D is very, very less than lambda. So this radiation pattern and gain will not be the performance parameter. So in this case, we can propose new models for near field region. Okay. So here I will show you few models. Okay. So the new propagation models, new methods to estimate the tag detection. Okay. So this equation typically used for RFID system. Okay. So this equations comes from the Friis equation and combination of forward link and the reverse link. Forward link is actually when we transmit a signal from RFID reader to RFID tag. Reverse link is this tag will re-radiate that signal. Okay, so re-radiated signal again will receive by the RFID reader. So this link is called reverse link. Okay, so for calculation we can do for forward link and reverse link, then we can derive this equation. Okay. Okay. So this equation is actually for far field region. So if we are working at near field region, this equation will not be used for RFID system. In this case, we evolve a new parameter which is power transfer efficiency. Okay. So we can obtain a qualitative tag detection prediction on the basis of simulated result of the RFID reader. Okay. So this is actually the modeling, or we can say reader antenna and tag coupling. So reader equivalent circuit voltage, this is actually the generator. VG is the actually voltage generator, okay, and 50 ohm is the internal impedance. So we can model any RFID link through this. Okay. So this is actually the Z parameter, which can tell us how much coupling is there. So this is actually the mutual coupling of antenna when it is in the near field region. So power transfer efficiency parameter is helpful to get the performance of antenna in the near field region. Okay, so Z matrix we can find out from this, and based on the Z matrix we can find out the power transfer efficiency. Okay, so it can be computed. It is not a very difficult task. It is just a ratio of power. So it is actually I square R, okay, which we know very well. So if you see, I have put some comparison. So if you see results which are obtained from different platforms. So this is first result is actually received from CST Microwave Studio. Second one is the measurement result. Third one is achieved from the MATLAB, and fourth one is from the RFID reader. So if you see all the results, these results are more or less similar. Okay, so the field distribution we can get from any tool. Okay, so this is the comparison so that we can use any of this tool, or we can compare the performance in the simulation which is actually done in CST or in MATLAB, and we can verify through measurements. Another application is actually the guided propagation. Okay, till now we saw the propagation in air, because RFID link was what we have discussed till now, which was actually in the air. Now the same thing we can do for the guided media. Suppose we have some tunnel or maybe pipe. Okay, we can put some RFID tag inside and we can detect it. Okay, but detection in this scenario is different from that scenario. So we will see here some theoretical formulation. Okay, so this was forward channel. We put a tag inside the metal pipe. Okay, and we are just make a reader antenna here. So we are just transmitting a signal, and this signal will reflect back. Based on that, we can find out the communication. Okay, so this forward channel link and reverse channel link, we can make a theoretical formulation for that. So that we have mentioned these lot of parameters are involved in this communication. So I will not discuss. I just mention in this PPT. If anybody is interested, you can refer this PPT. So this is the reverse link, and previous one was the forward link. Okay. Performance of a tag at high temperature. Okay. So if suppose we are using our RFID tags where temperature is very, very high. Okay. So that we have to measure the performance of the chip. Okay. So actually here we are measuring we are putting a RFID tag here, and we are measuring the read range from the RFID reader antenna. Okay, so what we are doing here, we are changing the temperature of this chip. Okay, so we have this machine, we can change the temperature. By changing the temperature, we are finding the read range. Okay, so what happens if we change the temperature, the read range will change. Okay, so this is actually, this measurement tells us the reliability of this chip. This chip will work at high frequency or not. Okay, so these kind of measurements are necessary when we have application of high temperature. So this is just as an introduction that if we want to use the tag or chip at high frequency, then we have to high temperature, then we have to do such kind of testing. Okay. So okay, we finished this part. If anybody have any question, then you can ask. Otherwise, then we will go for the next topic.
Hello.
Yes, ma'am.
Good evening, sir. Sir,
Good.
when we are doing the
SAR analysis, how much voltage we should apply on the port for the microstrip antennas? So
Okay, ma'am, you have freedom that you can apply any voltage, but whatever you are applying, you will put in the equation. Okay, so that you will get the same SAR value for each voltages. Suppose you are giving 1 volt or maybe 1 watt power, then you will get some SAR value. If you are uh, transmitting 2 watt, then you will get different SAR value. But the result of SAR will be same.
okay, for the any voltage result of the SAR value will be same.
Yes, the SAR value will, whatever the calculation you will do, sigma E square by rho, the value will be same.
As I'm getting the SAR value 15, 16 for 1 volt of excitation. As I've seen in many papers, they applied the zero point 0.1 volt.
Correct.
So by reducing the voltage, can we get the lesser SAR value?
No, ma'am. Actually, what happens, this SAR value which you are talking about, it is not exact value, right? Some value you will get after calculation, whatever the value you will get, based on that, you will find out the SAR, which is actually we use in PT max. So when you will find out the PT max, it will be same.
Okay, that will be same.
Okay. Yeah, PT max will always be same. SAR value may be different, but you are applying higher voltage, you will get more SAR, definitely. But when you will find out the PT max, that will be same.
PT max will be same. And
Yes.
by using PT max, we will going to calculate the original SAR value.
Correct, correct.
Okay, sir. And sir, there is one more question.
Yes, ma'am.
Hello. Sir. Sir,
Yes.
as you said, the values for the electric conductivity and the second parameter is
Dielectric
density.
constant.
Density. That is different
Okay.
for
Yes,
different frequencies. As I am,
correct.
if I am designing the UWB antenna, in that case, I am having the larger range. And then how I will get the data for the higher values for the density and is there any source or anything that there I will get the density parameter for 5 gigahertz for 10 gigahertz like that?
Okay. In this matter, I actually when we did this kind of research, then we found some data sheets. Okay, but if you see the biomedical engineers, those are not working very high frequencies like UWB frequency band. So you may not get the exact value of conductivity and dielectric constant at high frequency. It is actually tested and available at low frequency, maybe up to 4 or 5 gigahertz. But based on that, the behavior of dielectric constant and conductivity, you can make some assumption
Okay, sir.
that what value will be changing. So you have to simulate your antenna at some different frequencies band, maybe 400 or 500 megahertz band gap, so that you have to do some simulation at maybe 10 or maybe 15 steps.
Okay, sir.
Yeah,
Huh.
because
Thank you.
there is no measurement. Actually, these values which I have shown, these are actually measured values. The density, material density, and the conductivity and the dielectric constant of these tissue layers. These are actually the measured one. But the biomedical engineers, those are not actually working on very high frequencies, or maybe nowadays I cannot say, but I can find out some sources where we can find out these values. If I found any value at frequency, I will share with you.
Thank you, sir.
Thank you.
Thank you, sir, for your
Yeah, thank you.
support.
Hello, sir. Good evening.
Yes. Yeah, good evening.
Sir, can we measure SAR value in a laboratory?
Yes, ma'am. It is actually not an easy task to measure the SAR value. If you see in India, where we can measure this SAR value in maybe 1 or 2 industries are there.
Yes, sir.
So this SAR value measurement is very difficult or very means not available in institutions. So I don't think any institute can measure this SAR value.
Okay.
You can go. I have one video of SAR measurement. I can share with you.
Yes, sir.
Or
Yes.
you can just type the SAR measurement. It is actually the Italian company. Okay, where they have this SAR measurement. So this is not actually easy. That's why institution don't have this kind of measurement facility.
Okay.
But nowadays, if you see these electromagnetic softwares, those are very powerful. We can find out the almost exact value from the simulation. But again, we have to have this knowledge of how we are simulating the thing, because this simulator can give anything.
Okay, sir. Thank you. Thank you, sir.
Hello.
Yes, ma'am.
Yeah, hello. Hello, Dr. Rajesh. It's Dr. Rashmi
Yes.
from IIT Nagpur.
Yes,
And
ma'am. Hi.
this is really, yeah, hi. This is really wonderful session, and you have actually given lot many information to the researcher. Like my question is, as you said, generally the wearable antenna used for the low frequency means not in the not more than or not even for the UWB range or the super wideband range. I have gone through many papers where the researchers are actually make this antenna for the super wideband range for the biomedical application, body wearable antenna for medical application. The range is UWB or super wideband, but they have not mentioned all these values which you have mentioned, like the dielectric constant and the conductivity values. And without that, they have done the SAR analysis and they have shown the result. So my question is, that SAR value can be considered as a value which is a true one, or what is your suggestion on the same?
Okay. So in this way, ma'am, what we can do if we don't have these measured values or the correct information of that, we can do some trials. Maybe we can develop these antenna. Okay, then we can put on a human body. Then we can get the measured result. On that basis of measured result, we can do some changes in the simulation. So we can go some reverse way of result. Okay, so
Okay.
in this way we can make some characterization like that with the help of measurements. In this way, we have to spend lot of time, but in
Yeah.
this way we can get the actual situation.
Right now, like in the scenario of 5G and the IoT, lot many people are actually going for the UWB range for the body wearable application.
Correctly.
So again, the SAR analysis will be difficult, and if we follow this method, then it will be even more difficult because we will not get the values for all the ranges,
Yes.
right?
Yes. Yes.
So in that case, a normal SAR analysis with the help of simulation will work.
Uh, you can refer some maybe at low frequency. Suppose you are making this antenna at 2.4, right? You simulated some SAR value, and by doing something you got some measurement at 2.4 gigahertz. Okay, on that basis you can go for higher frequencies as well, and you can justify your results at high frequency with the help of low frequency, that it is working and you are getting the same things in the measurements.
Okay,
Then
fine.
only we can say. Otherwise, it is very difficult. Yes,
Yeah.
in simulation, even it is very difficult.
Yes, right. For simulation, it will be very difficult for the high
Yes,
frequencies, right?
yes.
Thank you. Thank you so much,
Yeah.
Rajesh.
Thank you, ma'am.
Yeah.
Any other participant?
Dear sir,
Yes.
normally people are working on that FHS software.
HFSS software. Yes.
So
Yes.
does this results vary with that simulation tool, or it is what is the relation, sir?
No,
Because
no, sir. No, actually, whatever the software you are using. So if
uh-huh,
you see HFSS and CST, both are very powerful tool.
uh-huh.
So if you design any antenna or any circuit in these software, results will always be same.
Acha, okay.
Results only change when we don't have full information of these softwares.
Oh.
Suppose there are various things we have to tell the software, so that software will give result on the basis of what we are giving. Sometimes what happen when people don't have full information of software, then they may get different result. Then they can say, sometimes the people say that HFSS is better or CST is better.
Right.
So both softwares are same. Those have very powerful these electric magnetic field calculation tools. So these give same results.
Oh. Yes. Thank you.
Yes. Anyone? Then we can go for next topic, which is actually a unique topic, which is not very usual. So I will go for this active antenna. Okay. So many times we have studied or we have listened this active antenna term. So pupils confuses with this active antenna. Okay. So pupils call active antenna as they generating some signal from power amplifier, and they can connect one antenna with that. So they call this whole system as active antenna. But in real sense, this is not actually active antenna. The active antenna definition is actually different. So here you can see one passive antenna. Here we can have no amplifier in this circuit. But in this active antenna, we have one amplifier unit. At least one amplifier unit should be there. And this antenna should be a part of this circuit. Okay. If there is no antenna, then this circuit should not work. Then only we can say that it is active antenna. So in active antenna has two roles. One is the radiation, okay, which is radiating power from, it is collecting some signal and it is transmitted to the air. Another function is to transmit that signal to this amplifier circuit so that this circuit will complete. Okay, so this thing we will see in the next slide and it will be more clear. So this theory part I will skip it. So in this case, this is actually the oscillator circuit. So we all know the oscillator circuit where we have one active device. It may be BJT, FET, MOSFET, whatever. And then we have one passive element here. Okay. So in conventional oscillator circuits, we have this LC network and this is amplifiers.
आहे की नाही दिसलं नाही होतं तर तरी
Okay. I request to participants kindly mute your mic. Okay. So in this case, on the case of oscillator, in this case, what we are doing, we are replacing this LC network by a patch antenna. Okay. So this antenna here, it will radiate some signal and it will transmit back some signal. Okay. So in this case, this oscillator needs two things. So Barkhausen criteria, we all know we have to fulfill the Barkhausen criteria, then only this circuit will oscillate. So the Barkhausen criteria is the loop gain of this circuit should be 1 and the loop phase will be in multiples of 2 pi. So loop gain A beta should be 1 so that amplifier can give some gain, maybe 14 dB, 16 dB gain, then there will be some loss in this circuit. So the total value which we are getting in this whole circuit, A beta should be 1. Okay. So in this case, we are using patch antenna. So here we can see these are 2-port device. Okay. Normally antenna is having a 1-port device. But in case of active antenna or active integrated antennas, antenna must be having 2-port. So this is actually not a common antenna. So this is, you can see here, this is 2-port patch antenna. Okay. So this is designed actually, there is no standard design equation for such kind of antennas, but we can have some idea. So there is some length and width of this patch. Based on the length and width, we can find out the resonance frequency. Okay. So this is actually the electromagnetic coupling. So we have this amplifier circuit here, amplified signal going from here to here. It will couple to this antenna. This antenna will radiate some signal into air and it will transmit back that signal so that in the feedback side, this amplifier circuit will receive that signal and again this will work as a oscillator circuit. So this is the idea. So this patch antenna here is serving two functions. One is the radiation, another is this feedback path. Okay? So in this way, we can call this full circuit as an active antenna. If we remove this antenna, this oscillator circuit will not work. Okay? So this is the real definition of active antenna. People call active antenna by putting some switches. Okay, they put some RF switches like pin diode or PN diode or some other varactor diode, and they call that antenna as active, but that antenna is actually the passive, although they are using the active element like pin diode or varactor diode. So active antenna definition is we have to we are amplifying some signal. So steps to develop active integrated antenna. It is actually the application of this kind of antenna is, suppose we are in a space where we don't have RF power. Okay, because we have to supply an RF power to antenna, then only antenna will work. In this case, in active antenna, we can give some DC supply and this antenna will resonate. Okay, so we don't need to supply any RF signal to this circuit. So in space, if we don't have RF power, we can generate that RF power through active integrated antennas. So the DC value from where we will receive, we can use energy harvesting circuits. So in environment, there are a lot of electromagnetic signal. We can receive the energy from that electromagnetic signal and we can use that energy as a DC, okay, by using the energy harvesting circuit. That DC we can use for this oscillator circuit, so that we are actually using the energy from the environment. So these are the steps how we develop active integrated antenna. So initially we can develop first the feedback element, which is actually the 2-port patch antenna. Then we will implement an amplifier circuit. So amplifier circuit is same as we all have studied in our bachelors. This is amplifier unit, which is maybe BJT or FET, whatever. We have to give gate bias, drain bias to this circuit, and in this way we can make an amplifier circuit. Then we can integrate this amplifier circuit with the passive element. Okay? So this is the full design of this active integrated antenna. Here we are using some filters. So I will discuss this filter. What is the use of these filters? If you see, okay, I want to show you some graphs if I have. Okay. So these filters, these are actually band stop filters. Okay. Why we use it? If you see this patch antenna or this amplifier circuit, if you see the S11 of this patch antenna, okay, like this. So this is the S parameter of microstrip patch antenna. Okay, so it is resonating at around 5.2 gigahertz. Let's say if this antenna has some other resonances, maybe at different frequency like here or here. So whenever you develop any antenna, you may find some other resonances as well. Okay, so at low frequency, if antenna having some low resonance, then it will create a problem in active antenna circuits. So what we will get here, we have to put band stop filters so that we are blocking the 5.2 gigahertz signal which is going to here, so that other frequency signal will go into this filter and absorb here. So for absorbing purpose, we are using here 50 ohm resistor. So by using 50 ohm resistor, we can receive the power from the other frequency components. So the frequency component which will go inside this circuit, it will be a design frequency, which is 5.2 gigahertz. So this is the use of band stop filter. If we are not using this band stop filter, if there is any resonance at low frequency, which is actually not the desired resonance, then what happen? This oscillator circuit may oscillate at that frequency. Because if you see the gain curve of the amplifier circuit, the gain at low frequency is higher, and as we go from low to high frequency, the gain reduces. So because of the higher gain of this device at low frequency, this circuit may resonate at low frequency. Okay, so this is actually the protection of that circuit. So this is the full simulation. This simulation scheme, actually we have did this in ADS software. So there is another software which is advanced design system. So all active circuit things we cannot do in CST and HFSS. We have to go for ADS circuit. Okay, so amplifier design, any oscillator design, any mixer design, we have to go for ADS circuit. So here we are seeing the loop gain. Loop gain is actually 1 at design frequency, and loop phase should be 0. Okay, 0 or multiples of 2 pi. So in this way, in the simulation, we can say that this circuit may oscillate. Okay, second simulation is oscillation power. So we can see at 5.2 gigahertz how much power this circuit is transmitting. So this is actually 9.2 dBm power this circuit is transmitting. So in this way, we can develop the active integrated antenna as a signal generator. So this is a small signal generator. So this, in this picture, you can see here, this is actually the microstrip patch, and here this is the amplifier circuit. So combining the amplifier unit with this passive element, we can make an oscillator circuit. So this oscillator circuit is actually called active integrated antenna. So these are measurements result. So this is the peak you can see here. This is the oscillation peak. So the spectrum analyzer result is this. So we can see the spectrum in spectrum analyzer, so that we can see this antenna is resonating at less than 5.2 gigahertz. So it is designed actually at 5.2, but it is resonating at lower frequency. So there are some other factors are there. Because of those factors, it is resonating at low frequency. So this is some different maybe other function we can include in the passive radiator. Okay, so instead of doing oscillations, we can do some more functions with the passive radiator. We can make polarization reconfigurable antenna, so that we can switch left hand circular polarization into right hand circular polarization, or maybe linear polarization. So by using RF switches, we can switch the different polarization. Okay, so this is the freedom we can achieve in the passive circuit side. We cannot do any changes in the active part. So by changing this connection, or we can give some supply to these diodes, different supplies to these diodes. So these diodes may switch on or switch off. So based on that, we can switch the polarization of antenna. Also, we can switch the radiation pattern of antenna. So here you can see there are two patch elements are used. So radiation pattern in one state, it is going like this. In another state, it is going in the zenith direction, which is actually the normal direction. And another state is having 30 degree. Okay, so we can switch the radiation pattern in different directions by doing the switching. Okay, so for switching, we are using here pin diodes. So we can make switch on or switch off these diodes. Based on that, we can find out the pattern configurability in active antenna. So what is the application of these kind of radiation pattern switchable antenna? Suppose we want to use this antenna as a wireless charger. Okay, so wireless charger, we can switch the beam, so that suppose we have multiple devices where we have to charge it, we can switch the radiation pattern, so that our multiple devices can be charged by doing this kind of operation. And this is not mechanically reconfigurable, this is electronically reconfigurable. So it is very easy to switch the bias. So simultaneous wireless information and transfer. So here we have three blocks. One is the energy harvesting. Whatever the energy in the environment, we can harvest it. We can use this energy for the wireless power transmission. So by using active integrated antenna, we can use this energy harvesting DC value, and we can transmit the RF signal. Okay. Again, after transmitting this signal, we can use this backscatter communication, which is RFID. Okay. So by doing all these things, we are using the supply from the environment and we are transmitting signal from our circuits. So this is actually the communication. So for this communication, we don't need any battery. Okay? We can have a very efficient this energy harvesting circuit, then we can make efficient this wireless power transmission circuit. So we can use some energy from the environment and we can do the communication. But for that we need to make some efficient circuits. Okay? So if you have any question, you can ask. Am I audible to all of you?
Yes, sir.
Okay, so then kindly ask questions. I know that this is not very common topic. This is a different topic because very few people are working on these kind of technology in India, like active integrated antenna, but it is very useful topic.
In wearable antenna, sir.
Yes.
Sir, in front of dipole antenna, we are using a V-shaped structure.
Instead of using the dipole antenna, you are using V-shaped structure, right?
No, sir, no, sir. In one of
No.
the design, in front of a dipole antenna, a V-shaped structure was there.
Mm-hmm.
So, sir, why we are using that one, sir?
In my slides?
Yes, sir. Yes, sir.
Okay, so you are talking about that variable antenna, which is actually straight dipole. Then we made folded. This. Right?
Yes, sir. Yes, sir. This one, sir.
Okay.
This
So you
V-shaped
are
structure.
talking about this.
Yes, sir. Yes, sir.
Okay. So this is actually the design how we proceed from straight dipole to this kind of layout. So this straight dipole, if you see this length LD, so this length is actually divided in these arms. So the total length A plus B plus D and plus C, it will be similar to LD. Okay, so the length will be more or less same, but we make it folded because we want more magnetic field along this plane. Okay, so in this way, if you see the surface current will travel from lower to the upper part. Okay, here also you will see from surface current from here to here. But in this surface current distribution, you will not get any magnetic field here. Okay, so the magnetic field value will be very, very low. So we want to increase the magnetic field. That's why we make this structure like this, folding structure, so that the surface current will move like this, so that we will have more magnetic field or strong magnetic field along this loop. Okay, so whatever the object near to palm, we can detect through this magnetic field. This another structure we have added. This is folded arm, and this is used as a director here. So if you see the size or length of this this length of this we can say parasitic element, which is less than this driven element. Okay, which is the actually the concept. So we are going with the concept, but we are making this thing compact. We are just making it like bending here so that our this whole circuit can be fitted in a small size. So this element is used as a director here. So the confinement of field in along this fingertips. That's why these kind of directors we have used. Also, if you see with one director or two director, we are not achieving very good values. When we put one reflector, then we can see that the radiation is confined along the fingertips. So the reflector, the role of reflector is more in case of Yagi-Uda antennas.
Okay, sir. Okay, sir. Can I ask one more?
Yes,
clarification?
yes. Yeah.
Sir, yes, sir. Usually, sir, in Yagi-Uda antenna, sir, that directors are less than that normal antenna, that radiator.
Yes,
The,
correct.
the height is lesser, but here in this case, sir, that it is more. So, is there any specific reason, sir, for that?
No. You are talking about the director size or director length is less than the driven element length, right?
Right, sir. Right, sir.
So if you see this length, the length from here to here, it is less than this length. It is less than this LD. Don't see this picture, okay? Don't see this picture that this length is less than this length.
Yes, sir. Got it, sir. Got it.
Yeah. No, if you are seeing this structure like that, you are saying that it is bigger, but it is actually the smaller compared to this. And you can treat these as wires. Okay, so here only one dimension you can tell. So we are considering here only the length. So length should be less.
Okay, sir. Got it, sir.
Yeah. Okay, any other question? Okay, then other thing or like hands-on sessions we will do when you people will come in offline sessions. Then we will show you how we calculate these values, SAR values in software and active antenna. I can show some designs so that you can get all these things right in practical sense. Okay, so if no other question, then I think we can close the session.
So it was a great session, sir. Hello.
Yes,
I'd
please.
like to express our sincere thanks to Rajesh sir for this informative lecture. You have given a very clear idea on wearable antennas as well as their application in terms of healthcare sector or defense area. Then we were reintroduced to some biological concepts like clean tissues as far as EM wave is concerned on these areas. Then we have seen the RFID system and their application. We also discussed some design challenges on wearable antenna. Then we were lucky to see some actual prototypes of these wearable antenna and their testing also. Then we were introduced to a whole new technology of textile antennas and their mathematical modeling also. Then the guided propagation for EM waves and active antennas were also discussed. So it was a quite interactive session. Many participants discussed their queries related to SAR values and other antenna related questions. So this will surely inspire many participants to explore themselves in the wearable antennas field. So thank you, sir. Thank you once again.
Thank you very much, and I thank all the participants who joined here and asked questions. And we will be more happy when you will join the offline sessions. So we will have more interaction with you.
So there is a last question, if
Yes,
possible.
yes, ma'am.
Sir, as you said, for FR4, there will be the different values for the density and conductivity. And for then,
Yes.
if we were considering the RT-Duroid material, is it different values for that, or it will be the same nearby?
Ma'am, if you talk about the density, then
Yeah, yes, sir. Conductivity and density of the material.
okay. So if you see the FR4 material or this Roger material, because these are dielectric materials, so ideally it should be 0, right? Tan delta should be 0. but their construction is different. So the FR4 substrate will have more 10 delta, or we can say that more lossy compared to the Roger substrate. Okay. So the construction, which is actually we talk about the micro level like molecules, then the construction is different for both material. So epsilon R is also different for both materials. You can get FR4 for maybe 4.3 dielectric constant only, but you can get Roger substrate for different dielectrics. Okay, it is available 2.2 dielectric constant is available, 2.3, 2.6, up to 10.2 dielectric constant is available in Roger. So actually the manufacturing process is different, and also the loss tangent is different. So that's why this Roger substrate is very costly, because the loss tangent is very less. So if you use Roger substrate at 100 gigahertz, you will have less losses in that substrate. But if you are using FR4, then losses will be very high. There are
Okay,
some
sir.
Yes.
Yeah, actually, sir, I'm just asking about, as you said, when we are considering the SAR analysis and we are
Mhm.
considering skin, layers of the skin,
Mhm.
and any conductivity and the effect, due to the effect of the dielectric constant of the material, what
Mhm.
will be the conductivity and density of the skin layer, of the fat layer, and the
Mhm.
third layer was muscle layer? Is
Mhm.
that changed for each and every material?
No, ma'am. No, ma'am. That is actually different. The human
At
body,
every frequency, yeah.
yes, for different frequency, it will be different.
Huh.
Yeah,
But for different
but
material, it will be same.
yes, if you are designing your antenna on FR4 or Roger, the
Hmm.
same effect you will feel when you put on a human body.
Okay, sir.
Yeah, the performance of the original antenna will not change. In that way, if you are seeing that epsilon R may be different or substrate may be different, but the effect from human body or the tissue layer effect will be same for both dielectrics.
Okay, sir.
Yeah.
Thank you, sir, for your wonderful session. Actually, I'm from the many reasons, I'm just thinking of where to ask these questions and how will I get the answers for that. And from this session, I got the answers for my questions that I'm working on. And thank you for your wonderful session and wonderful guidance that you have given to me.
Yeah, ma'am. If
Thank you,
you are
sir.
working on this topic, then you can means communicate with us, because we are also working on these kind of topics. So maybe
Yes, sir. I will sure I will I will contact you just as I will get your mail ID and
yes, yes. Okay, thank you, ma'am.
thank you, sir.
Okay, so thank you very much for all. Good evening, everyone.
Yes, sir. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you so much. It was a nice session.
Yeah, thank you very much, sir.
Sir, I hope to simulate live sessions on Monday, maybe.
Yes, yes, definitely. We will have a hands-on session from Monday, and it will be more interactive and it will be more interesting.
Sir, laptop is allowed for participants?
Yes, 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 you can come with your laptop. So we
Yes.
have some software, maybe student edition, so you can install the software in your laptop also.
No, sir. I have already license copy, sir.
Okay, then it's fine.
Okay, sir. Thank you so much. Thank you, sir.
Yeah, thank you.